So welcome to CS50 week 4 section on memory. And today we're going to be diving into memory, pointers, working with files, and all to get you more familiar with what C can do as you prepare for future weeks. So if you're new here, I'm Kelly. I'm the preceptor here at Harvard. So I run the college course, and there's my email if you ever want to contact me. Okay. So what are we going to be talking about today? First, some questions that might have come up for you in lecture are, what are these new things called pointers? How can we become familiar with their syntax? What is dynamic memory? How can we use it? And how can we read and write data from a file? So we're going to talk about all of these things here today, one by one. And as a preface, we're going to talk a little bit about hexadecimal notation to get you comfortable with seeing numbers that are written, addresses that are written in hexadecimal. So as a quick review, for this week's problem set, it's probably going to be helpful to understand hexadecimal notation. And hexadecimal numbers are usually indicated by a 0x in the front. So when you see 0x some number, that is usually indicative of the fact that it's a hexadecimal number. In hexadecimal, unlike base 10 where you have only numbers 0 through 9, you also have A, B, C, D, E, and F, corresponding with 10, 11, 12, 13, 14, 15, respectively. And so hex notation is usually used for representing addresses in memory. This base 16 system is not too different from what you've seen before in the base 10 system that you use on a daily basis. So when you normally see a number like 15, in your head you very quickly are doing the same sort of 10 to the 0, which is 1 times 5, so I have 5, and then the 1 is in the tens place, so 10 to the 1. And so instinctively, all of us, when we see the numbers 1, 5, we'll think, okay, 10 plus 5 is 15. Hexadecimal is the same logic, but now instead of base 10, we're using base 16. And the same goes for binary. Binary is just the same logic applied to base 2. And so when you see a hexadecimal number, for example, here we have 0x and then 3 or 4 bases, you can apply the same logic where the one on the right will have 16 to the 0, so whatever number there times 1, and then whatever number is in that next place here times 16 to the 1, and so on and so forth. So I'll pause here for any initial questions on hexadecimal. Couldn't we go to 37 with A to Z or even capitals? I have 48. Yeah, and so it's really a question of what is efficient to represent in memory. So hexadecimal is great because it is pretty compatible with the number of bytes that we usually like to store. And so as you'll see in a second here, for example, 255, which is a commonly used number to represent RGB values for representing color, can be easily represented as a hexadecimal number. And so, yeah, these are just decisions that were made a long time ago, but are very compatible with the amount of memory that we're typically using. Okay, great. So if I look at a hex value of color and I see other letters like H, is there a different base system for representing color? Yeah, so that might just be a different system that is representing those colors. But in this P-set, you'll be using the RGB system of representing colors. Great question. Okay. So from that, we're going to move on to pointers and talk a little bit more about what that means, what these are used for, and how you might have already actually been using pointers all along, but you didn't necessarily realize. Okay, so this chunk of memory might be something similar to what we've seen in lecture here. And so this is really just an abstraction of what is going on in your computer, but hopefully it gives you a bit of a visual to see what is really going on here. And so you can imagine this is, we have a number of bytes in our memory here, each with an address, just arbitrarily starting from 0x08 all the way to 0x1f. Normally we also don't really care about what these addresses really are, and they're normally not going to be this simple when you're actually working in your memory, but this is just to demonstrate. And so if we, for example, want to create an integer called n, we might have that look a little bit like this. So if we recall, an integer takes 4 bytes. We can see here that we've allocated 4 bytes to this integer n that stores the value 4. And so you can also see that this integer has an address associated with where it is in memory. And so what is the address of n here? 0x08, as we can see on this diagram. And so we learned some new syntax to represent this, and if I wanted to get this address, we can use this ampersand. So ampersand n means like the address of n, and we can see here that that's equal to 0x08. So next we have this idea, this new idea of a pointer, right? So we have int star p equals address of n. So what just happened with this line of code is that I created an integer pointer. So that's just another variable, but it's of type integer pointer. And that's what we can see here with this blue rectangle. It's called p, and it's storing the address of n. So we use ampersand n to get the address of this n variable, and we're storing it in our pointer variable p. Okay, so let's just go over this syntax a little bit more deeply since it's new here. And so when you see this first initializing statement, we're initializing p, int star here is referring to the type. So it's just another type like int, float, char. Now we have int star to indicate this is going to be an integer pointer. This ampersand refers to the address of a certain variable. So we have ampersand n giving us the address of the integer n. And then we can see here we have another new piece of syntax. So this star p equals 9. What's important to note is that the star here is not being used the exact same way as the star we just saw a second ago with this declaration, right? So this star means go to or dereference the address stored at p. So look at this address, 0x08, and then go to that address. So we're looking now at 0x08, which is where n is stored, and then set that value to 9. So I've now changed the value of n without actually modifying n itself. Instead, we just modified it using the pointer. So again, this star here is what we call dereferencing. Dereference or go to the address that is stored in p. Okay, so as a summary, type star is a pointer that stores the address of type. So type could be an integer, type could be a character, type could be a float, etc. Ampersand x gets the address of x, where x is some variable. And star x goes to the address stored at the pointer x. So in this third scenario, the X is referring to some sort of pointer that we have, and star goes to the address that is stored at that pointer. Okay, so before we do this practice, are there any questions about pointers? Okay. How did the address numbers get chosen? They all seem pretty random. Yeah, so when you actually go and look at what the address numbers that are being stored in your computer are, they do seem pretty random to you, but the computer has a system that manages which parts of memory should be dedicated to which pieces of code, right? So if you recall from lecture, David mentioned the heap and the stack. The heap is where the memory that you dynamically allocate comes from, and the stack is used for the local variables that you initialize. And so the computer does all of these things for you. You don't really necessarily need to think about it yourself, but it's helpful if you look at lecture to know which pieces of memory, how that's organized, so that you know where those numbers are coming from. Yeah, great question. Okay, so let's do a little bit of practice here and see. We have a little piece of code on the left here and a little visual of 3 bytes of memory. And so basically, I would encourage you to pause here for a second and just think, at the end of this piece of code running, what will the final values be for each variable or pointer? So I'll give you a second to think. You can put your answers in the chat. All right, so hopefully you've thought about this a little bit. We have some people putting some of their thoughts in the chat here. So let's walk through it together. Okay, so line by line, we're gonna see what's happening to variables A, B, and C. So this first line is nothing new. We have integer A equals 28. So A is gonna store the value 28. Then B is going to store the value 50. And so these two pieces shouldn't be too new to you, but what about for this next line of code? We have int star C equals ampersand A. So maybe first I'll ask, what type is C? What's the variable type that C is going to be? Yeah, so it's going to be an int pointer, an integer pointer, and it's going to store the address of A. So as you can see here, now the address of A, which I just arbitrarily set as 0x12, is now being stored in C. Great. So then this next line of code, we have star C equals 14. So what is that doing? What is the star here doing? And which variable is that going to change? Any thoughts here? Yeah, exactly. So A's value is going to change. Why is that? So the star C is dereferencing the address stored at C. And so the address stored at C is our A variable. And so it's going to use that address, go to that address. So we see this address, go to it, and then change that value to 14. Okay. And then this next line, we have C equals ampersand B. So I'm reassigning C's value to the address of B. So we can see that here, it's now changed to 0x13. Okay. And then this final line, we have star C equals 25. So similar to what we just saw, I'm going to go to the address stored at C. So go to 0x13, and then set that to 25. Okay. So any questions about this exercise? These addresses are relatively arbitrary. In reality, they would probably be bigger numbers farther apart, since these are integers and pointers. Someone asks, why would you use this if you could set the value directly? Yeah, that's a great question. And so one example we saw yesterday in lecture was the swap function, where if you're trying to swap two values, you couldn't pass them in by value because that wouldn't change those values directly in a separate function. Like, it's out of scope. And so when we used pointers and referenced those, then the pointers were able to change the values in the main function, even though what happens in the function was going to be like not necessarily remembered after the function was done running. Okay, can pointers be used in a loop to change value of multiple integers? Yeah, definitely. Why do you say C equals ampersand B, but int star C equals ampersand A? Okay, yeah. So this line of code, int star C equals ampersand A, is just like the ones before it, right? We're just declaring a new variable. Instead of it being an integer, it's going to be an integer pointer. And so we're initially setting that value to the address of A, which is 0x13. And then when I do C equals ampersand B, we're just updating the value. So like I could have done like in A, or A equals 5 to update the value of A. The same way, we're just taking C, which is a pointer, and updating its value to a different address. So in this case, the address of B. I see. Okay, so someone asks, when star C equals 25, then is A also going to change to 25? Yeah, that's a great question. So because I've updated the address that's stored in C here to the address of B, it's no longer pointing to the variable A. All right, so now it's pointing to the variable B, and so when I do this dereference and I set it to 25, it's setting 25 for the B variable and not A anymore. Okay. All right, these are great questions. And okay, hopefully more clarity will come in these next few words. Can a pointer point to two things? No, a pointer can only store an address, right? One address. And so we did see that you can have two pointers storing the same address, so that would mean pointing to the same integer or variable, but you can't have one pointer that's pointing to two things. So that's a great question. Okay. Can you make a pointer array? Yeah, just like any other array of like integers or like floats, you can also do that with pointers. Okay, we're going to keep going now to talking about dynamic memory. Okay. So we were introduced to this idea of malloc and like getting memory from the computer. And basically, malloc is like asking the computer, hey, can I have this amount of memory allocated? And so let's say we, again, have this memory chunk here. And now I want to create a pointer, so an integer pointer called array per se. And I'm going to set that equal to the address returned to me from the malloc function. So malloc takes the input of how much memory you need. And so I'm going to say, well, I'm just going to store one integer for now. So give me whatever the size of an integer is, that much memory. And so that's 4 bytes, as we know. And so we can see in the memory here, we have our pointer called array pointing to a block of memory. That's the size of an integer. Okay. So then if I wanted 4 more integers here, I can update my malloc call to be malloc and then give me the size of an integer times 5, that amount of memory. So now we have 5 contiguous pieces of memory, like one after the other, and that's all pointed to at the beginning by the pointer array. Okay, and so if I wanted to update the first value in this array, I can use the same dereferencing notation where I have go to the address stored at array and then set that to 1. So I'm going to go to that first integer slot and set that to 1. What if I wanted to update the value for the next integer? What integer or what address comes after that? Yeah, so we can do some pointer arithmetic here. We can do star, so go to the address of array plus 1 and set that equal to 2. Right? So instead of, because these numbers are just, the addresses are just numbers, we can also do some arithmetic to them. So like you just add 1 and we're gonna go to the next. Right? Similarly, we can kind of do this with 3, this next third element. And so you can also use this bracket notation to refer to the third element in the array. And so on, we can update the next one to 4. And so another thing we have to remember when we're working with memory like this is that if we have some thing we're mallocing, so we're asking for this amount of memory from the computer. And so I'm going to say like, here's this array pointer, give me this amount of memory. And then it's also important to note that we should always check that that is not null. So if it is null, there's nothing to do, like the computer didn't have enough memory to give us, we should return 1. Then we might use this array pointer somehow, but at the end of that program, we always need to make sure that we're freeing this array, or freeing that memory that the computer has given us. Because otherwise, we're going to run into some memory issues. A few more memory errors that are pretty common, just like the one we saw, is what we just saw was failing to free every block of memory which we've malloced. So if I didn't have that free call at the end, then that would be a memory error. Failing to f-close every file we've f-opened. So we're gonna see in a second, working with files, we also need to make sure that we're dealing with that memory correctly. and also using more memory than we've allocated. So this might be an issue you've already seen working with arrays. If you have, say, an array of 5 elements and you try to access the array element at the 5th index or the 6th index, that doesn't exist, and that is going to cause an error because you don't have access to that piece of memory. Yeah, okay. So we're going to get into some practice here using pointers and using malloc. So we're going to write a function called concatenate. It takes 2 strings and returns a concatenated version of the 2 strings. Okay. So I'm going to move here to VS Code. Okay. Oh, okay, it restarted. Okay, we'll restart it. Someone says, can we start array from index 0? Yes, you can. Arrays are always 0 indexed. Okay. Okay, so I'm going to start out by creating second here. Okay, create concatenate.c. And we're first going to start by importing some libraries here. So I know that I'm going to be asking the user for 2 strings. Okay, so I'm going to include CS50.h, which gives us getString. I'm going to include standard.io.h. I'm going to include string.h and standard lib.h. Okay, so I'm going to start with this main function. And if we recall, I'm going to take 2 strings from the input. So I can say my first string is going to be getString, whatever the user gives to me. So maybe string 1 is this. Okay. And then I'm going to do the same thing for string 2. Okay. Right off the bat here, what are some training wheels that I can take off, given what we've learned this week about pointers? Yeah, exactly. String is a data type that we've defined at CS50, but in reality, what we learned this week is that this is actually a char star, so it's a pointer to a character. So I can replace that. And then we want to be returning our concatenated string, so basically the first string after the next string in one string. And that's going to be whatever the result is of my function. So I'm just going to call my function concat, and it's going to take in S1 and S2. So it's going to take in 2 pointers to some strings, and I'm going to store this result in this 3rd string. Okay. And then finally I can just print whatever I get here. So I'm just going to print S3. Okay. So we've set up the part of getting in the input from the user and calling this function that we haven't defined yet. So let's actually define that function. Okay. So the first thing to note with defining functions is, what is my return type going to be? What am I returning? Yeah, a string, which I can also write as a char star. So I'm going to say it returns a char star, and then what are the types of my inputs to this function? So we can see here that I hope that it takes in an S1 and S2. Yeah, exactly. So 2 pointers, each of char star type. So I'm going to say it takes in 1 char star called S1 and then 1 called S2. Okay. Okay. So within this concatenate function, we're going to need to do a couple of things here. So the first thing we're going to need to do is get the amount of memory. So get memory for this like third string. And how much memory do we need for this string? It's going to be based on the 2 strings that I get, right? 2 char stars. And so I'm going to get some amount of memory, and then that memory is going to be empty. So I have to then copy over the values from S1 and S2 to S3. After I've done that, then I can just return my new string, S3, which has the values from S1 and S2. Okay, so let's try this out. So I know that I want to set up a char star of S3, I'm going to call it. And I first need to get this memory from the computer. So I'm going to use malloc. But then the question here is, how much memory do I need to allocate? Okay. So I need it to be at least as long as my 2 strings here. Yeah, so I need the size of these 2 strings. So maybe I will actually get that first. So I'm going to say the length of the first string and the length of the second string. Does anyone recall, how do we get this length of 2 strings or 1 string? Yeah, Sterling. So this function that I imported with string.h here, I'm going to pass in S1, and that will give me the length of the first string. I can do the same thing for the second string. So now we have these 2 values stored in here. That helps us with allocating the right amount of memory here, right? So how much memory is going to go in this malloc input? How much am I going to ask for? Given that I now have length 1 and length 2. Yeah, so it's going to be length 1 plus length 2. And the reason we don't have to necessarily use size of here is because we know that the size of a character is just 1 byte. And so I could say like length 1 times the size of a char, but it's a bit unnecessary. So I'm just gonna stick with length 1 plus length 2. Yeah, someone asked, what about the null character? That's exactly right. And so we have to make sure that we actually allocate 1 more than these 2 lengths so that we accommodate the null character, and we make sure that it's copied over. Okay, so now that we've allocated the right amount of memory, now we need to copy over string 1 and string 2 into this new S3 string. Okay, so what might I do here? What might I use? Yeah, someone says string copy. You could do that. It's true. For now, maybe what I might propose is that we just have a for loop that copies. We're gonna first start out with copying the first string over. So I'm gonna start it at 0, and then how many times do I need a loop if I want to go over every character in S1? someone says string length. Yeah, length one, which is I have the length of my first string. And then I'm gonna do I++, great. And so here, I know that I want S3, some value in S3 to be updated. Which index should go here? What should I be indexing? If I want like the first value in S3, then the second character, then the third, then the fourth, up to, yeah, people are saying I, exactly. Okay, great. And then I'm gonna set this equal to S1's I value. So now I've basically copied over, let's say if my first string is the word cat, then my C is going to be copied into the first character of S3, then the A, then the T. And then this for loop is over. But then I still need to copy over the second string. So if my string 2 was house, then I need the fourth character of S3 to be H, and then O, then U, then S, and so on. So I know I'm going to need another for loop here. And I know that this is going to loop how many times? Length 2, exactly, yeah. Great. Okay, and then now the index is going to be a little bit different here, right? I can't do I again because that's just going to overwrite what I just wrote for the first string. So how do I set up this index so that it starts where S1 ended? Yeah, someone is saying lang1, so that's the length of the first string, plus I. Yeah, exactly. So if my first string was, say, 3 characters, then this would start at the third index, which is where the last one left off, and then go subsequently. So I'm going to then set that equal to S2's ith character. Okay. Am I done here? Am I missing anything from S3? Is S3 done and ready to return? Yeah, the null character. I need to include the null character so that my computer actually knows when this string is stopping. So at what index is the null character going to be at? Yeah, the last, which is going to be the length of the first, yeah, the length of the second. And so that will give us that final index. And we're going to set that equal to, set that equal to \0, which is that null character. Okay, then finally we can just return S3. Okay. Yeah, someone say I have to free. So I mallocked this, but I also have to make sure that I free it. And where should that free go is a good question, is because I malloc it for my S3, right? And then I'm returning S3 to the main function. And so I need it here when I print it, so I can't give it back just yet. So maybe I'm going to say here, I'm actually going to free S3 after I've printed it, after I'm done using it, then I can free up that memory. Okay. So I think we can try making it. Let's see. Okay, what error did we get here? Call to undeclared function. Rookie mistake. What went wrong here? What did I forget to do? Header. Yeah, I forgot to prototype my function. Exactly, so quick fix here. Let's see if it makes this time. Okay, looks good. String 1, you say David Malin. There we go, and it prints out David Malin. Okay, great job. Any questions about what we just did here? Okay. Okay, great. Okay, so we have a few questions about why are we even doing these things? What's the difference between a regular variable name and these pointers? And so the main difference is really just that the pointer variation, so like int star, char star, those things are storing addresses, not like the values that we typically are seeing. So those are pointing to addresses of variables that already exist. Okay. Okay, we're gonna do another exercise here, and it's gonna be less coding and more debugging, like what is gonna go wrong with spotting some of these memory issues. So we're gonna debug a program create.c that creates a file given as input at the command line. So if I run /create test.c, it's gonna create a file called test.c. But our code has 3 memory errors. Can you find and fix them? Okay, so I'm gonna come back here and we're going to, where's my terminal? Oops. Bring my terminal back here. And I already have create.c loaded up here. So let's take a look at what this is doing. Okay. So it takes in a command line argument here as like the file name. And so we're checking, did they actually include a command line argument? If they didn't, then we're just gonna print this error message and return. Then we're gonna get the length of the file name that they gave us. We're gonna create a new block of memory to store that file name. So char star called file name, and we're asking for the size of a char times the length of our file name. Then we're gonna check if that malloc failed. So if they didn't have enough memory for us, then we're just also gonna say malloc failed, return. Then we're gonna copy this file name into a block of memory for the file name. So sprintf. Yeah, so we're copying whatever was inputted at the command line into this newly created block of memory. Then we're gonna open a new file. So we'll go in depth into fopen in a second, but open this new file. We're gonna write to it, or just have it open to be able to write to it. And then we're gonna check if that fopen failed. Okay, so right off the bat here, we're missing a few things, but we're gonna run valgrind here. Valgrind create.c, or should be /create, and I'm gonna give it a in command line argument of test.c. And we're gonna see what that gives us here. Okay. So there's a lot of text, can be a little bit overwhelming to read, but we can pick out a few things that might tell us what's going on. So first we have an invalid write of size 1. Okay. And it's pointing us at line 16. So they're saying, okay, something might be going wrong here. We have 6 bytes definitely lost, 472 bytes still reachable. Okay. So any ideas about what issues we have? Okay, someone says we are not freeing, not closing, and using more memory than we allocated. Okay, so with this free, which block of memory, what variable do I need to free? It's wherever I do malloc. So yeah, file name, exactly. I need to make sure I free file name after I'm done using it. So I'm just gonna put it down here, free file name. Okay. And then we also are not closing this file, this new file that I've opened. So I'm gonna do fclose new file. Okay, and then using more memory than we allocated. What is going on there? Why am I using more memory than I allocated? So I pointed us to line 16, where I ask for the size of a character times the file name's length, and that is the length of my file name, potentially. So if I have like a length of okay. Yeah, not quite. So someone says the size, this should be size of char star. So we do want the size of a character since we're gonna try to store a string of length of the file name. But let's say my file name in this case was test.c, right? So that's test.c, 6 characters. So this would return 6. Is it correct that I only need 6 bytes to store that? So something that we saw in our past program was that we actually needed one more to count for our null character at the end. So if I update this to file name length +1, then that accounts for my null character. So if I make this again and we run /create test.c, okay, I'm gonna run valgrind and see. Now it seems like all heap blocks were free, no errors, and everything is well in the world. Okay. So feel free to drop in the chat if you have any questions about this. We're gonna finally move on to file I/O. So working with files, reading, writing, opening, closing, all that good stuff. So really, we want to know here, we're gonna work on this example of how might we copy the contents of one file into another file. So let's say, for example, we have in.txt as this input text file, and then we also have an output text file that we want whatever is in.txt to be copied to. And so those are their file names, in.txt, out.txt. We have like the file contents, and then we also have an address of the file. So these two things have their own addresses in memory. Okay. So this first line of code here that we got a peek of in /create was we have file star input equals fopen in.txt, comma r. So it's a lot of bits and pieces, but let's break down what does that actually mean. So input is the name of our pointer variable that we're creating. file star is the type. So again, it's like pointer to a file. And then we're setting that equal to the return of fopen. And fopen is going to return the address of the file that you're opening up here. And so you might wonder, like, how do we actually know what fopen is returning? This is a good chance to read some of the documentation that we have for functions like fopen. And so this is an excerpt from CS50's manual. It's also linked there, so you can feel free to go and read that. But it's a lot of, it's a bit cryptic, but more or less this is saying if we have file fopen and it takes in these two inputs. So the first input is a char star, so a pointer to a character that contains the path name. So in the last example, we had index.txt as that path name. Then it also has this mode. So the mode can be R if we're opening a file to read from it, W if we're opening a file to write to it, and A if we're opening a file to append. Okay. This function returns a pointer to a file representing the open file, and in cases of error, when the path name doesn't exist, it returns null. Okay. So that's all helpful information to know here. Another note that we've already discussed a lot here, that string is actually just an alias for char star. And so these pointers are, we've been using for many weeks now, but both represent the address of the first character in a sequence of characters ending with the null character. Okay, so let's say we've now opened up in.txt and we have this input pointer that's pointing to this file. This is like a representation where each of these blocks is a byte. And so we have one byte for lowercase h, then lowercase I, then exclamation point, and then our null character. So how do we actually get that information? How do we read it? Well, we can use fread. So fread takes in 4 inputs here. And so what do those inputs mean? Here we have $C, so the address of C, we'll talk about what C is, size of character, size of char, and then 1, and then input. So what does that actually mean? So the first thing is a pointer, so the address of the first byte of memory into which to read the data. So it's some address of a byte of memory, and that's where we're saying, okay, you're going to be reading from something, you should read it into this piece of memory. Then the next one is size, and so that tells us the size in bytes of the type of data to read. In this example we wanted size of a character. Then we have the number of those types to read at once. So how many of the size blocks do you want to read? In this case, we just wanted to do 1 character at a time. And then stream, which is the pointer to the file that you want to read from. In this case, input. Okay. This is going to return the number of items that we read. And so if an error occurs, or if the end of the file is reached, then this function might actually return a value smaller than nmem, which is, in this case, 1. So in this case, it could either be 1 or it could be 0. This would return 0 if there was nothing to read. Okay, so as a recap, this is the location that we're reading from, which is pointing to input. This refers to the size of the blocks that we want to read. In this case, 1 char at a time, and we're reading one character block at a time. And then this ampersand C is the location we want to store these blocks. And so we've actually set up here a character that's called C, and this is going to store one character at a time. So it's going to store H after the first F read. And then once we have that stored in C, how do we actually write it to a new file? For that, we can use fwrite. Here, the inputs are relatively similar. And so if we look at the documentation again, it's pretty much almost the same that we've just seen. So it's gonna, instead of reading from, or reading to a certain buffer, which we call, or this address, we're gonna be writing from that byte of memory. And then we're specifying how big in bytes the type of data is we want to write, how many of those to write at once, and then where we want to write to. Again, this function is going to return number of items that we wrote. Okay, so in practice we see once I have this C but that has been read to, then I can output it in this out.txt file. And so this is going to continue again and again. We have the input reading I into C, which is our buffer, and then writing from our buffer to output. So on and so forth until we reach the null character. So what we just saw visually is what this piece of code does in reality. So we can see we have opened in.txt, we're checking that it didn't fail. Then we're opening out.txt, also error checking. And then we create a character called C. That's where we're gonna be storing things. It's gonna be our buffer. And then while fread to the buffer C, and we're doing one block at a time from input, while that is not equal to 0, which means like while we're still reading things, while there's still things to read, we should fwrite from that character buffer to the output file. Okay, that was a lot. Any questions about file I/O, opening, closing? Okay, why is this useful in real life for programs? So yeah, this copy example might not be the most useful thing we see here, but in other ways, it's helpful to be able to like write things to files and read things from files, and you're going to be doing a bit of that in this week's problem set. Hopefully that gives you a better sense. But you can imagine that if you have like a very long file to work with, or a very long, like lots of pieces of data that you want to be written to a certain file, then it can be helpful to use some code to do that. Okay, we're gonna do one final exercise here. And we're gonna create a program called pdf.c that checks whether a file passed in as a command line argument is likely a PDF or not. And so something to note here is that PDF files, they start with a 4-byte sequence. So when you actually look at the bytes that are contained within a PDF file, it's going to start with these 4 bytes. Okay, so we're going to move back to VS Code here, and I'm going to code pdf.c. Okay, I'm going to copy over some of these so I don't have to write them again. But we're going to include CS50.h, And then we're also going to include standard int.h. That gives us access to some types. Okay, so I'm taking in a command line argument, which means I also should check that they actually gave me 2 command line arguments. If they didn't give me 2, then I'm going to print improper usage. Okay, and then return 1. Okay. So then once they've given me a file, the first thing I should do is open that file, right? I want to be able to see what's in it. I should first open it up. So similar to the syntax we were doing before, I'm going to have a file pointer called PDF, and I'm going to fopen. Here, the first argument is the file name. And so in this program, I'm saying that the user is going to give me the file name in the command line argument. So I can say argv1, right? So if we recall, PDF or /PDF is going to be argv0, then the name of the PDF is going to be argv1. I'm going to set that in read mode so that I can read from it. And then just like in their last example with that C character, that was our buffer that stored the thing that we read from, we want to store a buffer for these first 4 bytes as well. So I'm going to use, this is a new type here, but it's just another kind of integer here that is typically used for storing things like bytes. I'm going to call this buffer, and I'm going to make it an array of 4 bytes since I want to see those first 4 bytes of my PDF. Okay, and since I'm also checking this against these 4 bytes, it might be helpful for me to actually store this sequence here. So I'm going to call it signature. It's a PDF signature. And we're going to put those values here. 0x50, 0x44, whoops, and 0x46. Okay, so now that I've opened and I've set up my buffer, now I can read. So I just want to read the first 4 bytes. So I'm not going to put it in a loop. I can just read those first 4 bytes. I'm going to read it to my buffer. And then I know that I want it to be 1 byte at a time, but I want to read 4 bytes. And I want to read it from this PDF file. Okay. And then once I'm done reading it, I honestly don't really need this PDF file anymore. I've already gotten the information I need, and it's going to be stored in buffer. So I'm just going to close it. Okay. So now, at this point, I've read the first 4 bytes from PDF into my buffer variable here, my buffer array. And so I can just check that the 4 bytes that are in buffer match up with this signature. Okay. So I'm going to loop I equals 0, and I'm going to loop 4 times since I know that I'm just checking those 4 bytes. Okay. And then I'm going to check byte by byte whether those 2 things line up. So if the ith character or byte in buffer is not equal to signatures, then as long as there's at least one thing that's different, I can say pretty confidently that print not a PDF. Okay. And then I can just return 0 since we did that successfully. At what point do I know that I can return, like, this is probably a PDF? Thanks for catching that. Yeah, so if all 4 of these are correct, which means as long as this if statement doesn't return 0, and I go through this entire for loop, then I can say this is likely a PDF, and then return 0. Oops, printf. Okay, so we did that kind of quickly, but are there any questions about this? I can try testing it out. I'm gonna make PDF. Oh. I forgot to provide an input to my f close. I want to close PDF here since that's what I opened. Let me make again. Okay. So if I just run ./PDF, it's gonna say improper usage, you need to give me a command line argument. Let's say I use create.c, which we know is not a PDF. We're gonna say not a PDF. Cool. I'm just gonna like create some test PDF file here. Okay. So now if I test ./PDF with my test PDF, hopefully, oh, it says not a PDF. Okay. In that case, it might be that I have to upload my own PDF. But either way, hopefully this would work on a normal PDF. But I'm not going to test it for now. But you can try it on your laptop and try uploading a PDF and see if it detects it correctly or not. Okay. Any other questions about this program? Okay. Well then, with that, that's the end of CS50 week 4, section 4 on memory. Thanks for your participation in the chat and all your questions, and hopefully I see you next week.